The company got started in 2021. We thought this might be a 5 to 10 year basic research project to get any sort of foothold on this problem. It's turned out to have gone faster than we thought. And so now, in 2026, we are getting ready to turn these into medicines and get them in the clinic.
The first big unlock in the past year was we were able to build AI systems that really doubled our rate of discovery. For every dollar we invest, we get twice as many payloads out that have the pro-youthful effects we're excited about. Based on the back of that success, we started our third therapeutic program, now focused on the endothelial cells that line all the blood vessels throughout your body, really playing an important role in every tissue. And then finally, potentially most importantly, we declared our first preclinical candidate. This is the first medicine you can hold in your hand that we want to take forward and actually put into human patients. These systems can now predict with really high accuracy what actually occurs in the laboratory before we ever go run an experiment. They can explain the vast majority of the variation. We can then have the system generate a number of hypotheses, test those hypotheses in experiments, and retrain the model in a virtuous cycle. What we're watching is one of these systems navigating the hypothesis space of all reprogramming combinations. On the left, what you're looking at are the transcription factors the model is choosing to test at each cycle of the experiment in an embedding space. And on the right, what you're watching is the performance of the very best hits the model has discovered over each cycle of experimentation. We've historically had a couple therapeutic programs, and it felt like it was the right time to bring on a third. And in this latest program, we decided to focus on the vascular system that permeates all of our other solid tissues, and in particular, the endothelial cells. These are really the walls of the pipes through which all your blood and signal and circulatory system flows. Once we have a bunch of those old endothelial cells in a dish, we can introduce many groups of transcription factors into them, all at the same time. Because this worked pretty well, to our knowledge, we've now generated the largest data corpus of reprogramming in endothelial cells. In other companies, this might be the time where I pull back this curtain and show you a cool robot, maybe like a roadster spinning on a screen. I might land a rocket outside. In molecular biology, after you burn millions of dollars, what you get is a tube that looks like this, filled with our preclinical candidate, and it's mostly a clear liquid. So unfortunately, I don't have such an impressive demo, but I appreciate you guys letting me get away with a gimmick. We can actually demonstrate that we can make old cells regenerate like young ones do. If you cut an old liver in half, it does not regenerate very well. But young ones, miraculously, like Prometheus on the rock, heal perfectly in about a day. We can close that gap by about half with just one dose of this reprogramming medicine that I'm holding. Aged cells actually suffer damage when you eat high fat or alcohol. And young cells, it turns out, are incredibly resilient to this. And so we've also found that when we reprogram these aged liver cells, they become resilient the same way that young liver cells are. So this demonstrates to us we're not just rescuing one function that is impaired with age, but multiple, in the same way that making an old cell young would be expected to achieve. Now there's one more phenotype that I hid from you for a moment, and I saved it for last, not because it's most important, but because I think it's actually the most visceral. So what I'm showing you are some animals that have all just had a drink of alcohol, and the only difference between them is on the left, these animals are young, the mice in the middle are old, and when they have a drink of alcohol, they pass out for 8 to 12 hours, and they're severely sedated. Now, the mice on the right received a dose of our reprogramming drug well before they ever received this alcohol. And I'll let you judge for yourselves which animals they resemble.
All right, so we got to move that vial and the LMPs with mRNA in them from Jacob's hand in the lab into the clinic so we can copy the playbook that Eli Lilly and Novo took with GLP-1s by starting in narrower patient populations. For NewLimit, we're going to start in narrower indications of aging-related diseases. I'll go into what those are, and then eventually expand to much broader patient populations. So we'll start in alcoholic-related liver disease. This is, unfortunately, a really challenging disease for patients to get. To put it in perspective, if all we did was develop a drug for ALD, it could be worth $20 billion on its own. What is NewLimit going to look like next year with these plans in place? We'll have our first age reprogramming medicine in human clinical studies. We're also going to launch another cell type program, so we'll have 4 franchises underway after immune, vasculature, and metabolism. And if we look out just a few years, we plan to have 3 drugs in human clinical studies. Now, the most important slide is the team. We're up here presenting all the work that's really an output of all the people here on the slides, some of which are in the room right now.